that okay, that 3x is irreducible in 3x bar is irreducible in Z5x, but not in ZX. So this is wrong statement. Any degree 1 polynomial is irreducible in any polynomial ring. That is what is considered in the class. So in fact, 3x is irreducible in ZX. So this is correct one. Okay, so because this is degree 1 and it cannot be factored into polynomials with degree less than 1. Okay, so this was confusion. So our proof for p-test, mod p-test is correct, that if some px after px in z qx is irreducible, this was p-test for irreducibility. Irreducible, then px is irreducible in zx. This was one thing, and one more thing I left was, you can ask me your doubts.
Yeah, I thought the definition for irreducibility was that if there are any further factors, they can be up to associates. So if there is something that's a unit, then that
Yeah.
would not count as a factor, and that makes it irreducible. That makes the polynomial irreducible. Here, 3 is not a unit in ZX. So why is this
So,
considered
irreducible
irreducible?
elements and irreducible polynomials, I think they are different. So
I see.
this is
Okay.
irreducible polynomial. Okay, that is, it cannot be factored into two polynomials which are
Okay.
degree less than or equal to 1.
Okay.
Less than 1. Okay, strictly less.
All right, so
So
one more question then. So if there's an irreducible element, we know about irreducible elements that they, for example, well, okay, it's not true. Fine, nothing.
okay,
Yeah.
so our proof for p-test was correct. So no need to modify it. One more thing was left as an exercise. If you remember, x power 5 plus x minus 1 is, this was some question, irreducible, sorry, reducible. I gave you factors of this reducible in ZX. That this can be written as x square minus x plus 1 x cube plus x square minus 1, like this. But how to then look at it, means how to solve it. So at least if we, first of all, we want to look at if there is linear factor or not. If there is not linear factor in 5-degree polynomial, so only factorization of this kind left, 2-degree polynomial into 3-degree polynomial. Okay, so if you see the polynomial itself, if n is bigger than or equal to if n does not belongs to, okay, 1, n does not belongs to this set 0 1 minus 1, then n power 5 is mod of this is too big, I mean too big than 1 minus n, right? You can look the graph of n x power 5, and 1 minus n. This is okay. So when you take mod, this graph is looking like, so for n bigger, n outside this set, n power 5 is too big. Okay, this is n power 5, x power 5 graph, and this is 1 minus n or n minus 1, something. Okay, it is like here. At 0, it is minus 1. Okay, so f fn is not 0. Okay, why? Because n power 5 is and if you add this 1 minus, sorry, subtract 1 minus n, it will become minus n plus 1. This will be either positive or negative, but not 0, right? This can never be 0. So it has no linear factor. So such kind of factorization is possible 2 degree into 3 degree polynomial. If you have doubt in this, you can ask me. Is understood this one? Okay. So let f can be written as p into q. P and q are two polynomials where p is 2 degree polynomial. So we can write x square plus ax plus b x cube plus cx square plus dx plus e. Okay. Now we want to find the value of a, b, c, d, e, so that the product of these two polynomials becomes f. Okay. So this is easy. You can do this x power 5 plus x minus 1. So what will be the product of this polynomial? X power 5 plus uh, c plus a x power 4 plus we want x cube terms. X is d plus b plus ac. This is x cube. If I'm incorrect somewhere, you can correct me. I'm just taking product of this. Now we want x square term. So bc plus ad plus x square. Now we want x term. This is bd plus ae plus b into e, right? Now
Yes.
we will compare the coefficients and we'll find the value of constants. And now it is easy. If you see this last coefficient, constant term, b into e is equal to minus 1. This implies b e is equal to 1 minus 1 or minus 1 1. These are only possible solution for b and e because we are in integers.
Integers.
Now use them and you will find this factorization. So this is all from the last class I wanted to discuss first. Now in the second week, we will recall what has been done in the class for 10 or 20 minutes. Then we'll continue to solve exercises. Okay. So second week starts with this division with remainders. So what was the main theorem here? Well, if f and g is non-zero are two polynomials in kx, where k is field, then there exists unique q and r in kx polynomial ring such that F can be written as G into Q plus R, where either R is equal to 0 or degree of R is less than degree of G. Okay, this was uh, first statement. Similar, this is similar to what we see in the integers. Okay, but there we don't have such a degree relation in remainder. There we have modulus less than. Like for we want in that case R to be less than Q in integer
I know
space.
about Euclidean domains also.
Yeah, Euclidean domains. There we have some kind of valuation which works as either mod or degree, like here. So what is corollary of this was if f is a polynomial and a is some constant in field, then f is equal to 0 if and only if x minus a divides our polynomial f. Okay, so this was corollary of this, and then we had some prime factorization. Up to permutation, they are unique. Okay, like in integers, we have I think fundamental theorem of algebra or what arithmetic.
Yeah, arithmetic.
Yeah, arithmetic. So here also in polynomial cases, we have prime factorization where each of the factor will be some prime power. Okay, what are primes here in polynomial day? They are similarly defined, like only p and 1 they can divide p. P is polynomial. So next theorem was due to VAT, that if f degree of f is n, then f uh, has at most n roots in K, even after counting with multiplicity. Okay, so this after this theorem, two simple examples were given. Where first example was if x power n minus p belongs to qx, qx is rational number system, uh, rational number field q. This is irreducible. Irreducible will follow from Einstein criteria for irreducibility, and has no zero in Q. V of x power n minus p is empty. Okay, so what is p here? Note that p is a prime in Z. Which is subset of Q. Okay, so Einstein criteria you remember, right? Okay, so let me continue with it. The next example was this x power p minus 1 bar, this polynomial in ZPX. So what is the factorization of this? If you use group theory for ZP is a group. Okay, all of the elements will satisfy this relation. Okay, ZP star is,
This is true for finite fields in general.
yes, ZP star is, sorry, ZP minus 0, because ZP is field and this is group. ZP star with dot is abelian group. Okay, so by Lagrange theorem in group theory, every element satisfies this relation. x power p is equal to 1 bar for every x belonging to zp star, right? So what will be the factorization of this polynomial x power p minus 1? This will be product of x minus k bars, where k is coming from the zp stars. So k from 1 to p minus 1. Yeah, ask.
Yeah, so we could also say that under multiplication, it's an abelian group, but under multiplication without zero, it's also a cyclic group, right?
Yes,
For all finite
finite
fields.
for all finite fields, their group of units are cyclic. Okay, this is another theorem. You will find it somewhere. Currently, I don't remember. I think, yeah, I don't remember that right now. But this is, you are right. They are cyclic. These are cyclic groups. Okay. So if you see from here, from this factorization, if x is equal to 0, if you put x is equal to 0, what happens? On the one hand, you have minus 1 bar. On the other hand, you have minus 1 bar into minus 2 bar and so on into minus p minus 1 bar. And this is nothing but 1 minus 1 power of p minus 1 into p minus 1 factorial. And now I'm removing bar. Okay. So I'm writing mod p. So minus 1 is equal to, because p is odd, I'm taking, for example, p is a prime, so we can take p odd. Okay. Odd prime. Then this is p minus 1 for p minus 1 is just 1. So this is minus 1, p minus 1 factorial mod p. So this is Wilson theorem. Wilson theorem. That this p minus 1 factorial is congruent to minus 1 mod p. Okay. So this was an easy statement which is coming out of this factorization. So next thing was about polynomial functions. Given any polynomial, let's say in 1 degree, let me take f fx in kx. We can define a function from k to k. I'm also denoting it by let's say f tilde k to k, such that f tilde of some alpha, which is from the field, is nothing but f of alpha, evaluating the uh, polynomial at that a. Okay, so any polynomial will give us a function from k to k. If it is n variable function, it will give a function from kn to kn, right? Okay, so so there was counter example for, let's say sin x. Sin x also function from, let's say, r to r. So question mark is this polynomial function? Is this polynomial function? No. What is an argument for this?
For one thing, it has infinitely many roots.
Right. So similarly, cos x and cos x similarly follows. It is not. It is not. Okay. What about e power x? It has, I think, no roots in R, right? So how to discard this as a polynomial function?
Can we use the fact that it has a polynomial expand, like infinite polynomial expansion, so it could not be some finite polynomial?
Actually, every non-constant polynomial has some roots, right? In some field extension. But e power x has, I think, uh, if we go over complex numbers, it has roots, right? Over complex number, it has roots, right? Or
Yes,
not?
yes. And
What will be one?
um, just 1 second.
It has no roots over complex numbers too.
Let me check. Hmm. Yeah, it wouldn't, because sin and
It
cos are
has,
complementary. So
yeah. So it has no roots. It is non-constant polynomial. So it has no roots. So this is not polynomial. So let's go to next argument, which was given in the class. That it's about identity theorem. If we have n, okay, let me write it. Theorem.
but
Let
one, I have a question. Constant polynomials are also considered polynomials of degree zero, and
yes,
we did not define degree for an arbitrary function. So we don't know, like for polynomials of degree zero, they can have like no roots at all, and we can't
yeah.
say anything about the degree of e raised to x. So can we still use that argument that it doesn't have a root to say that it's
First
not a
of all, e
polynomial?
power x is not a constant.
Okay, and that's sufficient. Okay, yes.
Then it's, if it is polynomial, so it has some degree. Okay, so it has to have some roots in some extension, at least over C. But in the C also, it does not have any root. Anyway, so f and g, let's take two polynomials of degree less than or equal to n, and also suppose if f and g both take same values at n plus 1 points, n plus 1 points, or I should not say points, they take same values at n plus 1 distinct elements of k, then f is equal to g. Okay, a simple proof for this was that we can take f minus g. Okay, and it is still of degree less than or equal to n. So this polynomial f minus g should have at most n roots. Hypothesis implies, hypothesis says that f minus g has n plus 1 roots, because f minus g at this n plus 1 distinct points, fai is equal to gai for every I from 1 to n plus 1.
So it has to be the zero polynomial.
So f minus g is equal to 0 and f is equal to g. So a similar thing is actually given in the exercise for n-variable polynomials. We will look at them after some time, after this discussion is over. So next thing was given about algebraically closed fields. This was definition. Let K be a field and any polynomial, non-constant polynomial, if they have a root, then K is algebraically closed. If every non-constant polynomial in Kx has a root in K, then we say K is algebraically closed. So here was an example of complex numbers, and sir also proved in the class, but I'm not going to discuss that. C is algebraically closed. And R, Q, these finite fields ZP are not. For R, Q, and ZP, you can give for R and Q, you can take this polynomial x power x square plus 1 has no roots. For ZP, you can construct some 1 or 2 degree irreducible polynomial. Okay, so they are not algebraically closed. Check for them. So one more thing is left, that all the prime polynomial in Rx corollary was there. Okay, prime polynomial in Rx are precisely x minus c or x square plus ax plus b. Here, AP says that a square minus 4b is negative. Okay, so that it has no real root. So I'm taking discriminant negative just because we should not have a root in R. Okay,
So
so these are
if the field is algebraically closed, then it's also the splitting field for any polynomial with coefficients inside it, right?
no, not necessarily. For example, C is a okay, right? You are correct. But I was giving an example like if C is algebraically closed, it is known. And take some polynomial like x square plus 1 in Q. So what will be the splitting field for x square plus 1 over Q will be different from C.
Okay, but
If
Splitting field
Q
over
is a
what?
sorry.
It is
Q is a field, but is it algebraically closed? What's it?
Q is not algebraically closed. Right.
Exactly. Yeah. So if you have an algebraically closed field, then is it true that it is also the splitting field of any polynomial unit?
Yes. Yes.
Okay.
You are correct in that sense. Okay. So one more thing was left, but I'm not going to discuss. It was. Let me point out that I will stop from here. So if you have 2-degree polynomial or 3-degree polynomial over real numbers or over any field, they are irreducible if and only if they have roots in that field. Okay. We'll use the theorem that f of a is equal to 0 if and only if x minus a into some gx is equal to f, or if and only if x minus a divides fx. Okay.
So using that theorem, you will see that 2 or 3 degree polynomial, they are irreducible if and only if they have no roots. Okay, over R or over Q, over C, so everything is every irreducible polynomial is looking like x plus lambda, right? Because the every polynomial will split in C. Okay, so let me go to the exercises. So this is first question and the second big exercise. At K is field and we have a polynomial f, and we are considering this f0 and f1, which is related to coefficients of f, and we want to show this if x square minus a divides f if and only if f0 and f1 both satisfy a. Yes. A is root of both f1 f0 if and only if x square minus a divides f. So hint is given. Let's see what we can do this. Okay, if we do from this side, assuming that x square minus a divides f. This implies fx can be written as x square minus a into some gx, right? And we want to show that f0 of a is equal to f1 of a, both 0, right? So what to do for them? Can we produce f from f0 f1? Some relation about if we want, for example, F has also A0. F0 also has A0. So we do not multiply anything but add them. But in F1x we have A1, right? And we want with A1 A1x. So we multiply by x here. Are these two equal? Now we'll check for higher degree terms. What about, for example, A3? A3
Do
is
you
coming
think
from F1.
do you think taking derivatives would help?
First of all, we check if this is correct or not. Is this correct? Then we can go to derivative. So let's write here. This is A0, A1x, and so on, an x power n. And on the other hand, this side we have A0 plus A2x and so on. We don't know last term if it is even or odd. Okay. And this plus A1 plus A3x and so on. And we have x here, multiplied x, right? So first term we got A0 from here, A1x from here, right? Now we want A2x square, right? Here. A2x square will come from this side because A2 is here. So what if we change here square? So everything will be squared, okay? Like next term will be A4 x power 4, right? In place of x, this was f0 of x. If you replace by x square, all the degree here it will be multiplied by 2, right? So are we getting same thing? We wanted A4 x power 4 in F, right? And that we can get from here. And we wanted here let me write some extra term. A0 plus A1x plus A2x square plus A3 x3 A4 x power 4 and so on. We want A3 x cube. A3 is here, so we want from here also. If we change to x square here, then we'll get these are also squared. Okay, everywhere. So what we are getting, fx is equal to f0 of x square plus x into f1 of x square. Is this correct? You verify it, you will find that this is what is happening here. This is the relation between f0, f1. So now we come to the proof. So we are this side. We are proving from left side to right hand. We are assuming that x square minus 8 divides f, so that we can write fx is equal to x square minus a into some gx. Okay. Yeah. Okay. So we can write here x square minus a into some that gx appeared there is equal to f0 of x square plus x into f1 of x square. We can write any polynomial f in this form where we are taking odd degrees term together, even degree term together. So this is even degree term in f, and these were odd degree terms, but you can take x common. So this f1 is also now even degree term, right? So this is even degree terms in F, and all this is odd degree terms. So you can write any polynomial like this. Okay, so now
Any as in, even if instead of 2 we had some other prime in a slightly similar way, analogous way.
yeah. So in that case, we can, for example, let's say 3. Okay, so what we can write, any polynomial fx in this form: f0 of x cube, which are multiple of 3, plus x into f1 of x3. These are 3n plus 1 type degrees. Okay, plus x square f2 of x cube. These are 3n plus 2 type. So all integers can be divided into 3 parts: 3n, 3n plus 1, 3n plus 2. So this is the factorization corresponding to 3n's. This is corresponding factorization to 3n plus 1. This is for 3n plus 2, right? You can write like this. So constant term will appear in which class? In first class, right? Here. Because 0 is multiple of 3. So 0 degree term is appearing here, 3 degree term, 6 degree term in first part. Like this. You can factorize like this. Okay. Now, okay. So apart, let me delete it. This. Okay. So now you have polynomials both sides. In place of x square, replaced by a. Replacing x square by a, both sides. What happens? Left side becomes 0.
Becomes 0.
On the other hand, this side becomes f0 of a plus x into f1 of a, right? Now this is some constant, this is some constant evaluated at a, actually f1 of a is polynomial f0 evaluated at a, this is some constant now, right? And because of this x, this total thing is polynomial. When it is 0, this implies f1 of a is 0 as well as f0 of a is 0.
We would need induction for this, right? We won't be able to prove it immediately for higher degrees unless we assume it for like x squared minus a, like unless we assume it for polynomials of lower degree, polynomials of this type of lower degree, x raised to p minus a. This last statement, would we need induction for it?
I think no. From in this step,
For, yes, this, but general, like right now we won't because we are only at degree 2, so we have already concluded it, but we were also considering an example where it was x raised to 3 minus a, for instance. So in that
okay.
case, or like a higher degree, so in that case we can use induction, right?
Actually, in our setting, f1 and f0, they are such that they are in 2 degree terms. If you follow this relation, we just need for 2. If it was the case for x cube minus a, for example, here x cube minus a, and f was some random polynomial, then f can be written as I just wrote f0 of x cube plus x into f1 of x cube plus x square into sum f2 of x cube. And if there were given this f0, f1, f2 like the same in the question, then you just evaluate at you can replace x cube by a and you will get 2-degree polynomial here, which will be just f0 of a plus x into f1 of a plus x square into f2 of a. Now when it is polynomial, this polynomial is 0 if and only f0 of a is 0, f1 of a is 0, f2 of a is 0. So these f1 and f0 is not random thing. They're coming out of f with this setting that this star holds. Right? Understood? So now if you say these steps are if and only if, or I can prove from other side. Okay, let me go line by line. Now we have f0 of a0.
So they were all
F1 of
equivalent transformations. At every step, the transformations were like equivalences.
equivalences, right? So this is given. Let me write it. Otherwise, there will be little bit mistake, I think. We want to show that x square minus a divides fx. But that Euclid's theorem implies that x square minus a into some gx or some qx plus rx is equal to fx. We can write fx like this. Now we want to show remainder is 0. This rx is 0. But again, f can be replaced by f0 of x plus x into f1 of x square, sorry, is equal to x square minus a qx plus rx. Here degree of rx is less than degree of qx. So here, if you again replacing x square by a, what we get f1 f0 of a plus x into f1 of a is equal to x square minus a qx plus rx. Here also you will just replace x square by a. This becomes 0. This becomes 0. This is 0 by hypothesis. So all that is left is rx, that is 0. This implies x square minus a divides fx. Okay. So here we have second question. When A is infinite integral domain and f, g, h be three polynomials where h is not 0 and f is equal to ga for all those points of an where h is not 0. And we have to show that f is equal to g. That is, by identity theorem for polynomials, it is enough to show that f is equal to ga for all of an. Then f will be equal to g. Okay. So okay, that is all we have to take care of. because A is integral domain. Okay, let me start with this. Since A is integral domain, AX is integral domain, right? And so R AX1, X2, AX1 to XN. Okay, these are all integral domains. This we have seen in first week. Okay, so now we come to a proof where it is given that, okay, let me use some notation here. V A, or let me not write A here, just V of H. This is same as those point of AN where H vanishes, and its complement I'm denoting by DH. Which is same as those points in AN where H is not vanishing. So what our hypothesis says that F A is equal to GA for all A belonging to DH, and we have to show that F is equal to G. Note that by identity theorem, look at this. If you just show that FA is equal to GA for all points of AN, it will be true for such a Cartesian product, but because this kind of Cartesian product is a subset of AN. And if you show for all points in AN, so you are showing a big thing, means identity theorem will hold there also. Okay, so it is enough if you show F is equal to GA for all point of AN, then F is equal to G. Okay, so this is our reframed question or rephrase. So what to do here? If you one more thing, what else identity theorem tells? Because these partial degrees are they can also be minus negative, means they can some xi can be 0 or all xi can be 0. Okay, so identity theorem, I'm just rephrasing identity theorem, which says that if f f of A is equal to 0 for all A belonging to some big Cartesian product which is bigger than the partial degrees. Okay. Subset of an, then f is equal to 0, where ni's are some big set. Ni's are subset of a with order of ni bigger than ri, where ri is degree of partial degree of f. Okay. So if you so if f is fa is equal to 0 for every a belonging to an, then of course this will imply that f is equal to 0. Okay. So we will use this kind of corollary, I would say, and we'll prove the our theorem. So rephrasing our this question again, if we consider t is equal to this that polynomial f minus g, then we have to show p is equal to 0 on dh, or for every a belonging to dh, then p is equal to 0. This is what we want to show, right? Look here. If p is equal to 0 for all a belonging to dh, then we have to show p is equal to 0. This is a reframed question. So, and we want to use identity theorem. What identity theorem tells is written here, but we use this corollary, which is direct consequence of identity theorem. If f is equal to 0 for all a belonging to an, then f is equal to 0. We'll use this. This is much easier than finding such a Cartesian product or such a box where f is 0. So we'll show that f is 0 on all a, and then f is 0. F itself is 0. So let's see how to do this. We have to show this. If we show p is equal to 0 for all a belonging to an, then p is of course 0. But let's continue from here. Let me define some other polynomial. Call it q, which is q of a1 up to a, is same as, I'm defining this, so pa, that is p1 pa1 to an into ha1 up to n. Okay, so what is happening here? What is so special about q? Q is 0 for every a1 up to an, belonging to an, right? Why? So there is two possibility. If first case a1 up to an belongs to ds, then h a1 up to an is not 0, but then f a1 up to an, sorry, p, I'm underlining this. So p a1 up to an, this is 0 on dh. And second case is when a1 up to an, this does not belongs to dh, or this belongs to vh, then h itself is 0. h a1 up to an is 0. In both cases, q is 0 by definition. Q is just product of p and h, right? So this is true for all an. We have shown this. This is our short frame. Now, since a x1 up to xn, this polynomial ring is integral domain. Okay, so once this is true for all an, this implies that polynomial q is 0 by identity theorem. Okay, polynomial, this polynomial is p, q is equal to 0. So because this is integral domain and q is equal to p into h, this is 0 polynomial. This implies either p is equal to 0 polynomial or h is equal to 0. Since h is not 0, hypothesis, this is from hypothesis, we have p is equal to 0, and this is what we wanted to show. This polynomial p itself is 0 on all. Okay, this is 0, that's all. This is how we show p is equal to 0. Now, because we had taken p is equal to f minus g, if you remember, we can go here. P is equal to f minus g. This implies, or this is if and only if f is equal to g. This was what we had to show in the question here. So I hope you understand. If you don't understand, you can look back twice. Okay. Okay, so let's see next. Map from ax to a power a defined by this. is surjective. If and only if A is finite field. Moreover, in this case, prove that kernel is generated by monic polynomial base. Okay. So I'm doing one. What is A power A? This is function from A to A.
Okay.
Maps.
Yeah. Okay.
So what is this doing AX to I A power A? This is just giving a polynomial function.
Yeah.
Okay. Phi of Px is
F. Okay. But why px? It's supposed to take in
P
the.
tilde. Where
It's
P
supposed to
tilde
take,
is not. Yeah.
why are we taking a polynomial? It's not in the domain, right? Only numbers, not numbers necessarily, but only elements are in the domains, and we have to assign them to a function, right?
Yes. So here we have polynomial,
Okay, correct. Huh. Okay.
and we
Then
want a function.
yes. Define that.
So phi of Px,
Mhm.
I'm writing as P tilde because of P.
Yeah.
Where P tilde is function from A to A.
Mhm.
P tilde of A is nothing but P of A. Okay.
Okay.
Polynomial functions, simple. So it is surjective means every function is polynomial function. So first, in this equivalence, first part is saying that every function in A to A, they're polynomial functions. And if and only if it is finite field. Okay, so if
Can I see the conditions once more?
Yeah.
Thanks. Is a function with So does the function compose with itself? I'm kind of confused about this notation, the way this function is defined.
we are taking polynomial f,
And it maps
and we are polynomial function defined by f.
right, and it maps to its own value, but at a.
Yeah, polynomial functions are from A to A only, right?
Yeah. That's fine.
That is what it is written.
Yes.
So A goes to fa is the polynomial function.
Okay, but what is this small a?
Small is element of capital A.
So, okay.
Small a goes to fa. Yeah.
Okay.
So for example, if A is infinite field, what will happen if A is infinite field? All functions are polynomial functions. Is this correct or not? Sin x is a function from, let's say, for example, R to R. But sin x is not polynomial.
Correct.
So this is not surjective. So it can, if it was finite field, I will prove for it. Sin x is a function map, but not coming from polynomial.
And for polynomials, this map is surjective?
If A is a finite field, if A is finite field, then it will be surjective. Any function will be polynomial function only. Okay? We'll prove it. How to show this? That if A is finite field, then let me write A is equal to A1, A2.
I think it will help us that these elements, the multiplicative group is a cyclic group. I think that would be really helpful because all the elements of the finite field can be expressed as x squared, x cubed, and so on till x raised to p raised to n, and
Correct.
they are the roots of the polynomial x raised to p raised to n minus x. So
yeah, you are right. So it can be written as 0 because we have to add 0. 0 is in that A. Other than 0, x square, x to the power some q minus 1. Q is prime power.
Okay.
Field can be any prime power. P is not there. After that, if you multiply x with itself, it will become 1. So this much is cyclic. Okay. So yeah, okay, nice. Now we will apply something. We will see. Let's say sigma is a function from A to A, and sigma of AIs is PIs. Now AIs are distinct. Okay, AI means just x power I plus 1. Okay. So this collection is, this is A0, this is A1, and so on. This A Q minus 2, maybe. Okay, write this collection as A0, A1, A Q minus 1. This is also similar to the same notation, so that we do not have confusion when writing this function. Sigma AI is BIs. BIs can be same also. Okay, AIs are distinct. This function can be multi-function, means multi-valued function, whatever, not necessarily one. So it is some function, and we want to see if it is coming from a polynomial. We want to see
the finite. Okay.
there exists f in AX such that
The finite field is also a vector space with respect with these as the basis, right? 0, 1, x squared, and so on till the final power of x. It makes a vector space over these, right?
no.
These as the basis. Sorry, with these as the basis, and over what though?
F p power r. This is field over FP.
Okay.
And there this is whole of f power p power r. This is whole of FQ. It is not basis. You can say it is generating set, but anyway. So we want to see if there exists f such that f a polynomial such that f of AI is same as sigma of AI, right? Then sigma will be a polynomial function. That's all we want. So we assume now A is finite field, and we want to show that this function is surjective. That means any function can be given by a polynomial function. So we are showing this part.
Why can't we see that FPR is a vector space over FP? Because multiplicative inverses are there for everything, and it's a cyclic group. So the multiplicative group is a cyclic group. So the entire FPR should be expressible as linear combinations of the powers of x. So then that would make it a vector space, right? Like with the.
But linear combinations means constants coming from FP, yeah.
FP.
So this is R dimensional space. So you should give R vectors in basis, not extra, not all of Q elements. In any case, if you have K subfield L, then L is vector space over K. This is true. And here FQ is vector space over FP. But this collection is all of, for example, FP power R. Not all the vectors are basis elements. No?
Yeah,
there will be some.
Yeah.
There will be some vectors which will form basis. Okay. So we come to the question which we wish. Sigma is some function. Some function. And we want to see if there exists polynomial such that f of A is same as sigma of A. I mean, sigma is a polynomial function. This we want. So we want f. So let f be A0, A1. Oh, we already wrote A0. So we can write B0, B1x, B fx is equal to B k x power k, such that f of AI is equal to sigma of AI. So if we can calculate these coefficients B1, B0, Bk's, then we are done, right? Okay.
Yeah.
So good. So now we write our hypothesis, which is given f of AI is equal to Bi. This coming from sigma. We want this, so we'll write it. Then first equation will become B0 plus B1 A1. Sorry, it is started from A0, so we can make it from A1, so that we are in good. A1, A2, and AQ. So this is B1 A1 plus B2 A1 square, right? Plus and so on. BK. Oh, sorry. Sigma is function, let's say. AI goes to CI, and we want. Yeah, this is right. So BK into A1 ka power K is equal to C1. This is nothing but F evaluated at A1. And this is nothing but sigma evaluated at A1. Right? So we got this polynomial. Next polynomial is B0, B1, A2 plus B2, A2 square plus and so on bk. A2k is equal to C2. This is nothing but sigma of A2 and this is nothing but f of A2. You got second polynomial. Now you will get similarly last B0 plus B1 A Q plus and so on bk AQ power k is equal to C Q. This is nothing but sigma of AQ and this is nothing but f of AQ. Correct? Now you have how many equations? Q equations.
So the usual laws of multiplication and distributive law will define what each polynomial maps to, or what any other function maps to. And it will always
Yeah.
be polynomial.
From here, if you see, what we want coefficients of f, then we are done. F and sigma will match. They will match. So we want to calculate coefficient of f. So we want to calculate BIs. But this system of linear equation can be written as 1 a1 square and so on a1 power k 1 a2 square and so on a2 power k. Last is 1 aq square aq power k this into b1 b2 bk. Sorry, it started from b0 is equal to c1 c2 cq. Correct? If you calculate these things, p1 b0 coefficients, then it is done. F and sigma will match, and sigma is just polynomial function, nothing else, right?
Yeah.
So
we can prove the linear independence by using some maybe Vanderbilt determinant or something, or maybe just induction.
So this is system of this form: a into b is equal to c.
Yeah.
Right.
Yeah.
And the determinant of a is nothing but, if you remember this kind of matrix, this is ai minus aj, I bigger than j, all such products.
Okay. Right.
And because ai's are distinct, this is not zero. So a is invertible, and b can be calculated as a inverse into c.
Okay. Yeah.
What is order of this matrix?
The same as the order of each. Well, at most we have. What was the order of the field?
Q.
So okay. So is it Q or Q raised to R? Just one second.
This is.
It's the same as the order of the field. That
Q cross k plus 1. You know?
Okay, that
and
way.
This
okay. I thought
this is
order
k plus 1 cross 1, and this is q cross 1.
Okay, I thought you meant like order as a group of matrices under multiplication.
Yeah, no, I was not asking that. Sorry.
Okay,
so
okay.
It is not a square matrix. So how to diagonalize? Sorry, 1 minute. This is system of this form.
If we see this.
So first of all, if we want, what we want actually, this is surjective, and it is given that it is a finite field, and k is depending on our choice. So if we take k is equal to q minus 1, then A is a square matrix. A is a square matrix of q cross q, and B is this matrix q cross 1, and C is also q cross 1. And in that case, this kind of matrices, A, 'A', determinant of this matrix A It's nothing but product of AI minus AJ. I is strictly bigger than J. And this is not 0 because AIs are distinct. So A is invertible matrix, and now you can find our coefficients which are BIs. B is equal to just A inverse of C. So F, so such a polynomial with coefficients B0, B1, Bk, we find such coefficients such that f of AI is equal to sigma AI. So sigma is nothing but a polynomial function. Okay, so sigma was a random function, and it matches with a polynomial function. So we can say sigma is also polynomial function on A. Okay, so this is how it is. On the other side, if we assume that this capital phi map is surjective, then we have to show that A is finite field. So we have already seen that if F is infinite field, then capital phi map is not surjective. Not all functions are polynomial function. For example, see here, sine function. Okay, so here I have written something. If cardinality of A is infinite, then cardinality of A is same as cardinality of polynomial ring over A. Okay, with one variable. But cardinality of A power A, this is bigger than cardinality of power set of A, and power set का cardinality is bigger than cardinality of A. So this capital phi map cannot be surjective. So better A should be of finite cardinality. So we can assume that A is finite, and we also assume that every map from A to A is polynomial, given by a polynomial. Now we want to show that A is a field. We already know that A is commutative ring with unity. Okay, we just have to show that every element, non-zero element, is invertible. Another thing is that finite integral domains, they're all fields. So it is enough if we can show A is integral domain, then it will be finite field. Okay, so if A is not integral domain, if capital phi map is not surjective. Okay, this is my claim, and I'm leaving it as exercise. So if I understand it, I will write in notes and update it. Okay, so check it. Okay.